Ever find yourself with like a million tabs open, juggling spreadsheets, videos, the works, and somehow your computer doesn't just spontaneously combust?
I think we've all been there.
Right. Well, today's deep dive is going to reveal the tech wizardry that makes it all possible, virtual memory. It's kind of like your computer has a secret stash of memory, making it seem way more powerful than it really is.
It's true. It's the magic that lets your computer run programs and store data, even when its physical memory, the RAM, is totally maxed out.
So, we're talking about our computers pulling off some serious illusions here.
Right.
Because our sources describe virtual memory as allowing computers to act like they have, get this, unlimited memory.
An apt comparison, actually. Imagine a magician, right, with that seemingly bottomless hat, the one, pulls out rabbits endlessly.
Oh, yeah, classic.
Virtual memory is kind of like that. It's all about clever swapping. It uses your hard drive as that extra storage space, like the magician's hidden compartment.
Okay, so instead of my computer throwing a tantrum when the RAM is full, it just starts, stashing things on the hard drive until it needs them again?
Exactly. And this whole process, it's called demand paging. Instead of loading a whole program into RAM all at once, the computer grabs only the bits and pieces, the pages of data, as they're needed.
So like streaming a movie instead of downloading the entire file. Smart.
Precisely. Efficiency is key here. But that then begs the question, how does it keep track of what's where? Our source mentions something called a present bit.
Right, a present bit. So is it like a little flag on each piece of data saying, hey, I'm in RAM, or nope, catch me on the hard drive?
You got it. Think of it as a super organized filing system, with the present bit acting as that label, letting the computer instantly locate what it needs.
Makes sense. But even with this clever swapping, eventually the RAM is going to be full again, right? We can't just keep adding stuff to the hard drive indefinitely, can we?
Good point. At some point, some data in RAM needs to be bumped back to the hard drive, making space for new stuff. This is where it gets even cooler. This is page replacement.
And this is where that modified bit our source mentioned comes in, right?
Exactly. Remember, efficiency is key. The system is smart about it. No point in wasting time saving data that hasn't changed, right?
Like if you're just reading a file, no need to hit save every 2 seconds.
Exactly. The modified bit flags if a page has been changed. Only modified pages get written back to the hard drive.
So we've got this whole system of organization and optimization going on in the background, like a million little elves making sure everything runs smoothly. But what happens when we're dealing with massive amounts of data? Our source talks about computers needing these huge address spaces to keep track of it all.
Absolutely. Modern computers have to deal with a mind-boggling amount of potential memory locations.
So we're talking like a library's worth of card catalogs, just to keep track of where everything is.
More like a library for every book ever written. Managing all of that requires enormous page tables. And get this, even those can get too large for RAM.
Wait, so it's like you need a card catalog to find the right shelf, but then you need another card catalog just to find the right drawer in the first one. My brain hurts.
It's like Inception, but for directories. And that's where it gets really meta. We start paging the page tables themselves.
This is blowing my mind. This incredibly complex system is running behind the scenes every time we use our computers. And most of us have no clue it's even there.
It's essential, though. Think about it. Editing photos, running complex software, even just browsing the web, it all relies on virtual memory.
It reminds me of trying to edit videos on my old laptop, the one with 2 gigabytes of RAM. It was a nightmare. Constant freezing, the fan sounding like a jet engine. Makes you appreciate a good virtual memory system.
For sure. And understanding how it works, it can even help you make better decisions about your tech. Like if your computer is always sluggish, it might not be about needing more storage space, but actually needing more RAM to handle all those pages efficiently.
So there you have it. Virtual memory, the unsung hero of the digital age. A system so complex, so crucial, and yet most of us never even give it a second thought.
It really makes you wonder what else is going on behind the scenes that we just take for granted.
Speaking of which, we only scratched the surface here. Even virtual memory has its limits, and researchers are always on the hunt for even more efficient ways to manage data.
Yeah, that's an intriguing thought.
Right. Maybe a future deep dive. But until then, listeners, I have one final thought for you. Imagine a world without virtual memory. Constant crashes, endless spinning beach balls of doom. Makes that RAM upgrade seem a little more appealing, doesn't it? Ever feel like your computer's playing hide and seek with information? Like it can't decide what to keep handy and what to stash away?
It's more organized than hide and seek, but yeah, there's a whole system for that. Today we're tackling page replacement algorithms.
We're going deep, folks, straight into how computers juggle information. And we've got excerpts from a real operating system's text as our guide.
Think of it like this. Your computer's memory is prime real estate, limited space.
Prime real estate, but not enough for everything all at once, right?
Exactly. That's where these algorithms come in, deciding what stays in immediate reach and what gets, well, kind of like put on a slower shelf.
So our source material calls it page replacement with fixed numbers of frames. Catchy, right?
In essence, fixed frames means limited slots, like a desk with only so much room for papers. Those papers, those are our pages, chunks of data.
Okay, so we've got our pages, our limited memory space. But computers don't just grab things randomly, do they?
Nope. There's an order to it, a reference string, like a to-do list telling the computer which pages it needs and when.
Ah, so it's not just what information, but when you need it, like following a recipe step by step. Now, our text throws out this optimal page replacement algorithm. Sounds like a dream come true.
It would be if computers could see the future. Imagine packing a bag perfectly without knowing the destination or what you'll do there. That's optimal replacement impossible in reality.
So no time-traveling algorithms for us. What do our computers actually use?
Let's meet the workhorses. First up, FIFO, first in, first out. Simple as it sounds.
Like the first person in line gets served first.
Exactly. Problem is, what if that first page, the one you need again soon, gets replaced just because it was there the longest?
Oof, yeah, that's frustrating. Like constantly reopening the same file because your computer keeps closing it. It's gotta be a smarter way.
There is, LRU. Least recently used. This one's got more memory, so to speak. It tracks which pages you've used lately.
So like it notices if I keep going back to the same document or app.
Exactly. It prioritizes keeping those frequently used pages handy, making your computer run smoother.
Okay, that makes sense when my laptop doesn't completely melt down when I have a million tabs open. But this all sounds very under the hood. How does it affect me, the average user, in everyday life?
Ever had your phone turn into a slug when you're juggling too many apps? Or your computer slows to a crawl when you're doing a million things at once? That, my friend, is page replacement, or rather, it's struggling to keep up.
So a better algorithm, a smarter one.
Yeah.
It actually makes our digital lives smoother.
Think of it like this. Would you rather have a phone that can keep up with you, or one that throws a tantrum every time you try to do two things at once?
No contest. I want a phone that can handle my multitasking madness.
Exactly. A good algorithm can mean the difference between a device that's smooth sailing and one that feels like it's constantly hitting speed bumps.
And to think, this is all happening behind the scenes without us even realizing. We've covered FIFO and LRU today, but I'm already wondering, are there even more sophisticated algorithms out there? What's the next level of memory management?
That is an excellent question, and one we might just have to dive into another time.
Something to ponder, folks. The world of computers never ceases to amaze. Until next time, keep those digital gears turning.
All right, so today we are gonna really get into it. We're talking computer memory
Oh, yeah.
and how your operating system makes decisions about what to keep readily available, like in that precious RAM, and what gets kind of shoved off into the,
Into the back corner.
the digital equivalent of that dusty box in the attic.
Exactly.
Hard drive storage, right?
Yep.
So we've got some fascinating material to dig into today, focusing on, get this, approximations of the least recently used algorithm,
Go.
LRU, if you're in the know. But and here's the thing, these approximations, they're not just some kind of like elegant computer science-y thing.
Yeah.
They have real-world impacts on how you experience technology every single day.
Oh, absolutely.
Yeah.
It's all about making you feel like you have unlimited memory, right?
Yes.
When in reality, we're working with
Constraints.
finite resources.
Exactly.
Oh,
Yeah, and I think most of our listeners, being familiar with, tech and how things work, they've probably heard of the least recently used algorithm, or as we said, LRU.
right.
The idea being that, what you haven't touched in a while, that's probably what's going to get, maybe moved off to the side.
Big sense.
But to track that with perfect accuracy, I mean, wow.
Yeah, that would be a lot, wouldn't it?
That's a lot of overhead.
Just imagine like having to keep a ranked list of every single file, every bit of data you've got.
Oh my goodness.
And it's changing constantly based on every click, every keystroke.
My computer's already working hard enough.
Right. The computational overhead would be
Intense.
immense.
Yes.
It would be a problem.
Yeah, so, computer scientists, being the brilliant minds that they are,
Mm-hmm.
they've come up with some really clever workarounds, ways to, approximate this least recently used idea
Right.
without bringing everything to a screeching halt.
Exactly. Get close enough, right?
Exactly, you got it.
Without having to, kill the performance.
Exactly, and that's what we're going to unpack. So first up, we've got the aging page replacement algorithm.
Okay, this is where it starts to get really clever.
Okay.
So instead of trying to remember every single access, we're just trying to get like a general sense of how stale the data is,
Okay, so instead of like a perfect, logbook of every time you looked at something, it's more like a
Yeah.
last access stamp that gets, a little more faded.
Yes. That's a great way to think about it.
Every day, something like that?
Yeah. So each piece of data in memory, it gets this thing called an aging register. Basically, it's a bunch of bits, right?
Yeah.
And every time you access that data, it's like you refresh the timestamp on it.
Oh, I see.
But, and this is key, over time, those timestamps, they kind of get shifted out as newer ones come in.
So the longer something sits there untouched, the more those timestamps fade away
Exactly.
until it's like, oh, I guess nobody really needs this anymore.
Time to make some space.
Time to make some space, right, exactly.
Yeah.
And this is where it gets really interesting because this actually relates to your experience.
It does.
Have you ever noticed, like, if you've got a ton of programs open, your computer starts to slow down a bit?
For sure.
That is in part because it's scrambling to manage all these aging registers for every single thing.
It's trying to make these really tough decisions about what to keep and what to potentially,
What to prioritize. Yeah, it's
Well,
like my
it-
brain during finals week.
there you go.
Some things are just a little fuzzier than others.
Right. You got to prioritize.
So it's not about perfect recall. It's more about getting a sense of what's been neglected.
Exactly. It's about trends.
The trends, yeah. Okay, so this aging page replacement, it's pretty slick.
It's elegant. Yeah.
But like, what happens if your computer makes the wrong call
Right.
and tosses out something that you actually need, 5 minutes later?
Yeah. Yeah. That's where the second chance algorithm comes into play.
Okay,
Think of it as like a safety net
got it.
for
Yeah.
those potentially premature evictions from RAM.
So it's not quite as ruthless as just booting something out the second.
Second, it's a little cold.
It gets a little cold, right? Exactly.
Exactly. So imagine like a pure first in, first out approach, right?
Right.
That's kind of harsh.
Yeah.
The second chance algorithm says, hold on a minute, let's just give this a quick check.
Right.
Instead of just immediately replacing that page, just because it's been a while, it gets a second chance if it's accessed again before its time is up.
So it's like your computer's like, oh, wait a minute. They just used that. Maybe I should hang on to it.
Exactly.
Just in case they need it again.
Yeah. It's like, let's not be too hasty.
Exactly.
Yeah.
I'm all about second chances.
Exactly. And this is really useful for data that might be used in bursts, Like you switch between tasks and suddenly you need something you were using earlier.
Oh, for sure. Yeah.
The second chance algorithm kind of recognizes that.
It's like that spice that you only use
Yes.
once in a blue moon. But then when you need it,
But when you need it, you need it.
you're like, oh, I'm really glad I didn't have to go all the way back to the pantry for this.
Exactly. Now, if we want to get even more advanced, we can talk about the third chance, or sometimes called the NRU algorithm.
Oh, okay.
And this adds like a whole nother layer of,
Oh, this is getting fancy. All right.
yeah, it gets a little fancier here.
Lay it on me.
This is about not just how recently something's been used, but also if it's been modified,
Oh.
right? So think about a document. You've got it open.
Mhm.
You've made some changes, but you haven't saved it yet.
Right.
That is way more important to keep in RAM
Yes.
than something you just looked at.
Because if you lose power,
Oh, disaster.
It's like, it's a difference between, remembering where you parked
Yes.
and remembering that you had to pick someone up on the way home.
Exactly.
One is a minor inconvenience. The other one is
It's a relationship test.
Exactly. Right.
Or-
Losing unsaved work,
Oh, it's the worst.
the worst.
So the third chance algorithm, it gets that right. It makes sure those modified pages, they stay in memory as long as possible.
They're protected.
They're protected.
Hmm.
We don't want to write them out to the hard drive unnecessarily
Makes sense.
because that slows things down.
Right, yeah.
We want to be smart about this.
Be efficient. It's like having a whole team working behind the scenes, tidying up our digital lives.
Right. Making sure everything's organized even when we're, maybe not so organized ourselves.
Exactly. It's like, I don't know, having one of those super efficient librarians who always knows exactly where that obscure book is.
Right. And they can get it for you in like 2 seconds.
You don't even have to see the Dewey Decimal System in action.
Exactly. And that's the thing, right? Just like a well-run library helps you find information quickly.
Yeah.
These memory management techniques, they're constantly working to make your computer feel responsive and efficient.
So all those times that I'm like, wow, that program loaded fast, or,
Yeah.
oh, that was a really smooth transition.
Yep.
I can thank the aging register, the second chance, the third chance, all those little helpers.
Absolutely. These little optimizations, they may seem small,
Yeah.
but they make a huge difference
They really do. It's amazing.
in the user experience.
It makes you think, though. I mean, we've been talking about how computers do this, but what about us?
Oh, interesting.
Like, our brains are dealing with way more data.
Way more data.
How are we deciding what to prioritize?
It's true. What are our little algorithms?
Right, exactly. What are our personal LRUs? That's something to ponder, I think.
It really is.
Yeah.
And it just goes to show, even when you're talking about something as technical as computers,
Yeah,
you end up circling back to the human element.
the mysteries of the brain. Well, on that note, I think we've covered some serious ground today.
We've delved deep
We have delved deep into the world of computer memory and how it all works.
and how it impacts our digital lives, which is
Which is everything.
pretty much everything these days.
Pretty much. So, until next time, everyone, keep those brains humming.
Keep those algorithms running.
And maybe pay a little extra attention to what your own memory decides to keep close at hand.
Indeed. Ever feel like your computer is juggling a million things at once?
It kinda is.
Like, how does it keep track of all the data, all the programs?
Well, that's what we're diving into today.
The unseen forces behind your computer's smooth operation.
We're talking page replacement
Your
algorithms.
page replacement algorithm sounds kind of technical.
It is, but it's what makes your digital life possible.
Okay, so break it down for me. What are these algorithms and why should I care?
Imagine this. You're working on your computer.
Already there.
You've got a bunch of programs open, maybe browsing the web, writing some code, listening to music.
Sounds about right.
Now, all that stuff you're working with, those programs, that data, it all needs to be stored somewhere.
My hard drive.
Well, yes, but also in your computer's RAM, it's memory. But here's the thing. RAM is a limited resource. Think of it like a desk. You can only fit so many papers on it at once.
Makes sense.
So when you open a program, parts of it are loaded onto your RAM disk. But if that desk gets full,
Time for some cleaning.
exactly. And that's where page replacement algorithms come in.
They decide what stays and what goes.
Exactly. They're constantly shuffling data between your RAM and hard drive.
So I don't have to.
So you don't have to. They make sure the most important stuff, the things you're actively using, are always on hand, right there on the desk. Or in this case, in RAM.
Okay, that makes sense. But how do they know what's most important? It's not like my computer can read my mind, right?
Not yet, at least. But that's where the concept of a working set comes in.
Working set is that like my to-do list?
Kind of. It's the set of data pages a program needs to have readily available in memory to run smoothly. Think of it like a chef's essential ingredients within arm's reach while cooking.
Got it. So it's constantly changing as I use different programs, right?
You've got it. And the algorithms we're talking about, they're trying to predict as accurately as possible what's going to be in that working set.
That sounds like trying to predict the future.
Exactly. It's like packing for a trip where you don't know the destination. One wrong guess and bam, page fault.
A page fault. Is that bad? What happens when you have a page fault?
Remember how we talked about RAM being like a desk? A page fault is like when you need a document that's not on your desk, you have to go to the filing cabinet, which in this case is your hard drive, and get it.
Oh, so that's why my computer lags sometimes.
Yeah.
It's fetching data from the hard drive.
Precisely. And hard drives are much slower than RAM, so those page faults can really slow you down.
Makes sense. So how do these page replacement algorithms actually work their magic?
Well, there are a few different types, but let's talk about two common ones.
Go.
First, there's the working set algorithm. It operates on the idea of temporal locality.
Temporal locality sounds complicated.
It's actually pretty simple. It just means that data you've used recently is likely to be used again soon.
Like how I always seem to misplace my keys in the same few spots.
Exactly. So the working set algorithm keeps track of recently used pages and tries to keep them in RAM. It's constantly adjusting, like a rolling window of the most recently used data.
So it's learning my habits as I go.
In a way, yes. It's trying to anticipate your needs based on your past behavior.
Pretty clever.
Yeah.
But you said there was another type of algorithm.
Right, the page fault frequency algorithm. This one takes a more reactive approach.
Reactive how?
Instead of trying to predict the future, It focuses on responding to page faults as they happen.
So it's like a firefighter, always ready to put out a fire.
Perfect analogy. If it sees a sudden increase in page faults, it knows the current working set isn't big enough, so it adjusts, grabbing more pages from the hard drive to prevent those slowdowns.
So these two algorithms, they're kind of like the unsung heroes of my computer, making sure everything runs smoothly.
Exactly. They're constantly working behind the scenes to optimize your computer's performance.
It's amazing how much complexity goes into something we take for granted every day.
That's the beauty of computer science. And here's something to ponder. As our programs become more complex and our data sets grow larger and larger, how will these algorithms need to evolve to keep up?
That's a great question. It makes you appreciate the work that goes into making our digital lives possible.
Indeed it does.
Ever find yourself with like a million tabs open, trying to run 5 different programs at once, and your computer just starts to like slow to a crawl?
Yeah, tell me about it. It's like trying to stuff an entire library into a backpack, isn't it?
Exactly.
Yeah.
And then you start to think, how do computers even handle all that information? How does it not just completely freak out? Well, today we're diving into the fascinating world of virtual memory to uncover the secrets behind how our computers manage to juggle so many tasks without completely falling apart.
And we'll be digging into some really interesting technical documents on operating systems to get to the bottom of this.
Right, like trying to explain how a magic trick works, but with, less smoke and mirrors and more ones and zeros.
Well, more like trying to explain how a really, really complicated clock works, with lots of moving parts you can't actually see.
Perfect analogy. So let's get this show on the road. To kick things off, imagine your computer's physical memory, its RAM, is like your desk. You've got a certain amount of space to work with, right? But what happens when you have way more papers and projects than your desk can handle? That's where the magic of virtual memory swoops in.
It's like having a secret trapdoor in your desk that leads to a massive library downstairs. You can't fit every book on your desk at once, so you keep the ones you're actively using within arm's reach and store the rest below.
Okay, that's a pretty cool way to think about it.
Yeah.
So virtual memory is basically like this clever illusion that makes your computer seem like it has way more memory than it actually does.
Exactly. Your computer borrows space on your hard drive to store the data that can't fit in RAM, kind of like using that downstairs library for extra storage.
Makes sense, but I've definitely noticed my computer slowing down when I have a ton of programs open.
Yeah.
Is that because of this whole shuffling act between RAM and the hard drive?
You're on the right track. Each time your computer needs information that's not immediately in RAM, it has to go fetch it from the hard drive, which is much slower.
So it's like running downstairs to grab a book from the library every time you need to reference a single sentence.
And each of those trips down to the library is what we call a page fault. Imagine how much longer it would take to write a paper if you had to do that for every quote or statistic.
Page fault, interesting term.
Yeah.
So more page faults basically mean more lag, right? My computer's just taking a stroll down to the digital library every few seconds.
That's exactly it. Each page fault adds a little delay, and those delays really add up, making your computer feel sluggish, especially if you're pushing it hard.
Okay, that makes perfect sense. So if virtual memory is supposed to make things smoother, how come it can also cause things to slow down so much?
Well, it's all about balance. Imagine trying to work on 100 different projects on your desk at the same time. Even with a magical trapdoor to a giant library, you'd still struggle to keep track of everything.
My brain just exploded thinking about that.
Right.
But yeah, you'd constantly be searching for the right papers, moving things around. It'd be chaos.
Precisely. And that chaos is kind of what happens inside your computer when it gets overwhelmed with page faults, leading to something called thrashing.
Thrashing, that sounds intense. Okay, so thrashing is basically what happens when virtual memory goes haywire.
Yeah. Exactly. Imagine instead of calmly walking down to the library to get your book, you're frantically sprinting back and forth, grabbing armfuls of random books and just shoving them onto your already overflowing desk, hoping one of them is the right one.
And that's basically what's happening inside my computer when I have like 50 tabs open and Spotify's blasting and I'm trying to edit photos all at the same time.
You got it. And all that frantic swapping between RAM and the hard drive, that's thrashing. It gets the job done eventually, but it's incredibly inefficient and wastes a ton of your computer's processing power.
Okay, so thrashing is bad news. But how do we avoid it? Is there like a magic formula?
Well, there's no magic bullet, unfortunately. But one crucial factor is how your operating system manages all this data.
Right. because it's not just randomly shoving data between RAM and the hard drive. There's a method to the madness.
Yeah,
Right.
absolutely. Data is organized into pages, kind of like virtual file folders. And here's where it gets even more interesting. The size of these pages can actually affect performance.
Hold on, we're talking about like bigger virtual folders versus smaller ones. Size matters even in the digital world.
Believe it or not, it does. Larger pages mean fewer trips to the hard drive, which sounds good in theory, but it can also lead to wasted space if you only need a tiny bit of data from a large page.
So it's a trade-off. Like
Yeah.
smaller pages might be more efficient space-wise, but then you're making more trips to retrieve them.
Precisely. It's all about finding the right balance for your system and how you use it. And to add another layer of complexity, some systems even use multiple page sizes to optimize performance even further.
Wow, that's pretty amazing. It really highlights how much thought goes into designing these systems that we often take for granted.
It really does. And as storage technology keeps advancing, who knows? Maybe the ideal page size will evolve, leading to even faster and smoother computing in the future.
Now, that's something to think about. It's amazing how much complexity is hidden beneath the surface of our everyday devices.
Absolutely. And understanding how those systems work can help us use our computers more effectively, even if we're not all computer scientists.
Well said. So next time your computer starts to feel a little sluggish, just remember the intricate dance of virtual memory happening behind the scenes, and maybe give it a little grace.
Exactly. It's doing its best with the resources it has.
Until next time, happy computing, everyone.